In question 2a, we have a diagram showing an electron at a point in a uniform electric field at an instant when it is stationary. In part 1 we need to add an arrow to the diagram to show the direction of the electrostatic force acting on the stationary electron. Well, the field lines show the direction of the force on a positive charge. The electron is negatively charged, so will experience a force to the left. In part 2 we need to state and explain what, if anything, will happen to the magnitude of the force acting on the electron as it starts to move. Well, the field strength is constant, so the force on the electron will not change. In B, we have a diagram showing a stationary charge in a non-uniform electric field. In B, we have two diagrams showing the same non-uniform electric field, one containing an electron, the other containing a proton. In part 1 we need to state and explain how the electrostatic force on the proton in figure 3b will compare to that on the electron in 3a. Well, the proton will have the same magnitude of force but in the opposite direction to that on the electron. In part 2, we're told each of the particles starts to move from the position shown. We need to state and explain how the magnitude of the initial acceleration of the proton will compare with that of the electron. Well, the initial acceleration of the proton will be much lower than that of the electron. They experience the same force, but the proton has a much bigger mass. In part 3, we need to describe and explain what will happen to the acceleration of each of these particles as they continue to move in the electric field. Well, the acceleration of the proton will increase as it moves right, so the field strength is increasing. The acceleration of the electron will reduce as it will move left, so the field strength is reducing. The acceleration of the electron will reduce as it will move left, so the field strength will reduce. In C, the line spectrum of neon gas contains a prominent red line of wavelength 650 nanometers. In part 1 we need to show that the energy required to excite neon atoms so that they emit light of this wavelength is about 2 electron volts. Well, photon energy is given by the Planck constant times the speed of light over the wavelength. Putting in the values gives an energy of 3.06 times 10 to the minus 19 joules. To convert this into electron volts, we divide by 1.60 times 10 to the minus 19, giving 1.9, which is around 2 electron volts is required. In part 2, an illuminated shop sign includes a neon discharge tube as shown in the diagram. A voltage of 4,500 volts is applied across the electrodes, which are 180 millimeters apart. We can assume the electric field inside the tube is uniform, and were asked to find the minimum distance a free electron would have to move from rest in order to excite the red spectral line. Well, the electron needs to move through 1.9 volts to gain 1.9 electron volts of energy. Millimeters to volt, well, there are 180 millimeters, over which there is a change of 4,500 volts, meaning 0.04 millimeters for every volt. We need 1.9 volts, and so this is a distance of 0.076 millimeters, which we could quote as 7.6 times 10 to the minus 5 meters.